In this problem number 7, we have a talk show that includes 4 women and 3 men. You know what I'm going to do here? Just so I can keep track of what's going on, I'm going to put them in an urn here. Well, let's say a box. Well, whatever. 4 women and 3 men. Okay, so I can keep track of what's happening. Now, here's part A. Let's look at part A. What are we going to do in A? A says that we're going to count the number of ways we can be seated in a row of 7 chairs. All right, no restrictions. We're just going to put them in a row of 7 chairs. So I'm looking at this. 1, 2, 3, 4, 5, 6, 7, right? Like we're in front of them. Jill's looking down, right? We're in front of them looking down at those 1, 2, 3, 4, 5, 6, 7 chairs. And how many ways can we do this? So I'm thinking we could put any one of the 7 people in this leftmost chair. Then once we have that person seated, we got 6 people left, right? We could put any one of those 6 people in that chair. Then we've seated 2 people, so there's 5 left, and we could put any one of those 5 people in this chair. Get the idea? And then 4, 3, 2, 1. We're going to multiply that, and that comes out to be 7 factorial. And if I computed that thing right, that should be this 50/40. Now in part B, what are we going to do in part B here? In B, how many ways can the panelists be seated if the men and women are to be alternated? Okay, so we have to alternate the men and the women. Let's draw our 7 chairs. 1, 2, 3, 4, 5, 6, 7. And let's look at some possibilities. Okay, so the men and the women have to be separated. So we're going to alternate them. So what if we tried this? What if we maybe put, say, a man here, a woman here, right? We have to separate them, alternate them. A man here, a woman here, a man here, a woman here. Now we've got what? 1, 2, 3 men. We've seated all the men. And now we have what have we got here? We've got, let's see, we've got a woman, a woman, a woman. So there's 1 woman left to be seated, and that woman's going to have to go here. But then if we do that, these 2 people here are not alternating. So this isn't going to work, right? That's just not going to work. We can't start out, apparently, we can't start with a man in that leftmost position. So let's rework this. Maybe 1, 2, 3, 4, 5, 6, 7. And let's try it this way. Let's put a woman in the leftmost position, then a man, then a woman, then a man, then a woman, then a man, and then a woman. And now I think that's going to work, right? How many men have we accounted for? 1, 2, 3. And how many women? 1, 2, 3, 4. We've got everybody accounted for. So now let's make our count. So what about this leftmost position? We're going to put a woman there, and we have 4 women from which we can choose. So we could put any one of those 4 women into that position. Then we come to this position. We're going to put a man there, and we have any one of those 3 men can go here. So that's going to be a 3. And now what about this position? Well, this is a woman. Now, we've seated 1 woman already. So we had 4. We've seated a woman, so there's 3 women left. So we can put any one of those 3 women here. And then in this position, a man. Now, we've seated a man already. We had 3 to begin with. We've seated 1, so there's 2 left. Now, this position here, we have going to seat a woman, and we have 4 altogether. We've seated 1 here and 1 here. So out of the 4, we've seated 2, so there's 2 women left. And we can put any one of those 2 there. And then what about this position? We're going to put a man here. Now we've already seated 1, 2 out of the 3 men. So there's only 1 man left, so we only have 1 choice for that position. And then finally this position, we're going to put a woman. But we've already seated what? 1, 2, 3 out of the 4 women. So there's only 1 choice for that position. So we're going to multiply these together. And if we multiply these together, we'll get 4 times 3 is 12, times 3 is 36, double 36, we get 72, double 72, we get 144. All right, and that's what we got up here for part B. Now, what are we going to do here in part C? So in part C, what do we want? In part C, we're looking for this. And how many ways can they be seated if there must be a man at each end of the panel? All right, so let's draw our seat. So 1, 2, 3, 4, 5, 6, 7. And we have to have a man at each end. So a man there and a man here. And then apparently it doesn't matter what kind of mix we have in here. So let's get this one right here. We got a man here. We got 3 men all together, 3 men from which we can choose. We just want one of them. So there's going to be any one of those 3 men can go here. So that's going to be a 3. And then what about over here at the end? Okay, we need a man there. We've already seated one at the left end. Now we have 2 men to choose from. So we have 2 choices here, right? Any one of those 2 remaining men. Now, we have, right, I'm back up here now. We have 7 people all together. We've seated 2 of them. So we have 5 people left. And there's no restriction here. So these people can be placed any way at all. So what about this position? Any one of those 5 people can go here. Then there's 4 people left, any one of which can go here. 3 people left, and then 2 people left, and then 1. So this looks like, okay, just to count it, it's going to be, say, 3 times 5 factorial times 2, or how about 6 times 5 factorial, which is, if you like, 6 factorial, which is 720. Or if you don't want to count that, just do this, just multiply them all out. We'll get 720, which is what we wrote for part C. Now over here in number 8, here's part A. Part A, we're looking at this. How many times bigger is, oh, that's a mess. How many times bigger is 9 factorial than 7 factorial? All right, so we're going to write this out. So let's write it like this. Here's 9 factorial, but we can write that as 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Now look at this part right here. That's 7 factorial. So in this part right here, 9 times 8 is 72 times 7 factorial. So how many times bigger is 9 factorial than 7 factorial? 9 factorial is 72 times as big as 7 factorial. So we're going to write this as 72. Now, in part B, we are asked, how many times bigger is n plus 2 factorial than n factorial? So let's use this idea here. So what we did here is we took 9 and broke it down to 9, 1 less, and then 2 less, 9 times 8, and then 7 factorial. So let's start with this n plus 2 factorial. N plus 2 factorial. Now we can write that like this. N plus 2, right? Then 1 less. So n plus 2 minus 1 is going to be n plus 1. And then 1 less than this. So n plus 1 minus 1 is just an n. Let's get it to right here. N. But that's what we're looking for here, right? Is n factorial. So we want an n factorial here. So here we are. So n plus 2 factorial is n plus 2 times n plus 1 times as big as n factorial. Or if you want to multiply it out, how about n squared plus 3n plus 2 times as big as n factorial. Now, as I read this problem here, we've got 5 houses in a row. So I'm going to draw those 5 houses. Just imagine this. You're looking at 5 houses. 1, 2, 3, 4, 5. And what are we going to do here? We're going to paint, or each one is to be painted with exactly one of these colors, red, blue, green, and yellow. Let me write those down. So we're going to get red, blue, green, and yellow. What else here? Okay, so in how many ways can we do this so that no 2 adjacent houses are the same color? Now, adjacent houses are one right next to each other. These 2 are adjacent, these 2 are adjacent, these 2 are not. So let's see how we can start this. let's maybe look at this leftmost house. Now, we can choose any one of these colors. That makes sense. Any one of these 4 colors is going to work for that first house. And then for the second house, right, we don't want the same color, right? We can't use the same color. So whatever color we choose here, we cannot choose here. So we had 4 colors to begin with. Maybe we chose one. Maybe it was green. So now we have 1, 2, 3 colors left for this one right here. Now we know this. This house is a different color than this house. So whatever color this house is, move to the next house. This house here has to be a different color. So whatever color this one is, this one has to be different. Now suppose we did this. Suppose this was red, and then this was blue. Then how many choices do you have for this one? Well, you can't choose blue again, but you could choose red or green or yellow. So we just can't have it to be the same color as this one. So we have 3 colors left. So this is going to be a 3. And then whatever color this is, this one over here cannot be that color. So whatever color this is, toss that one out. We still have 3 colors left. So this can be any one of 3. And then this can be any one of 3. So we end up with 4 times 3 to the 4th. 4 times 81, which is 324. Problem number 6 says a 10-digit combination lock can be set to open in any 4 digits. So here's part A. So we just need 4 digits to open this lock. Part A, here's what we're looking for. How many sequences are possible? All right, so we just want to know how many sequences are possible. There's no restrictions here. So the way I'm looking at it is we're going to have 1, 2, 3, 4, right? I like to do everything with these slots like I did over here. We've got, just imagine, here's the 4 numbers, right? The 4 digits, 1, 2, 3, and 4. And then let's just start someplace and start counting the number of ways we can do this. How many sequences are possible? No restrictions. So we've got 10 digits to choose from. I think we could choose any one of these 10 digits for that first number, any one of 10 for the second, any one of 10, any one of 10, and we multiply those together, we get 10,000. Now that's, of course, with no restrictions. In part B now, I think we are going to have a restriction. How many sequences are possible if no digits can be repeated? So this is part B. No repetitions. So 1, 2, 3, 4. And with no repetitions, how many choices do we have for this leftmost position? I think we could still choose any one of those 10. So this is going to be a 10. But now this one here cannot match this one, right? We want no repetitions. We had 10 to choose from to begin with. We chose one already, so there's 9 left. So we can choose any one of 9. And now, for this position here, we started with 10, but we've selected 2 already, and we don't want any repetition, so we can't use these 2. So we started with 10, we're down 2, so 8 here. Now we've used 3, so only 7 left. So we're going to make that multiplication, and that comes out to 50, 40.